Hello everybody. In today's lesson we're going to look at fluid flow through a pipe and the equation of continuity, and we're going to start our discussion with a review of the law of conservation of mass. So let's say we have a pipe and we have fluid flowing through the pipe at some velocity v. The law of conservation of mass tells us that the amount of fluid that enters the pipe in position 1 has to be equal to the amount that exits the pipe at position 2. Given that this pipe has the same cross-sectional area in both points or positions, the velocity of the fluid will have to be the same where it enters and exits the pipe. What we're actually saying here is that the volume flow rate of the fluid through the pipe is equal at points 1 and 2. So let's kind of unpack that a little bit. A volume flow rate can be expressed as the product of cross-sectional area and velocity. So in terms of the dimensions, if we're using SI units, we might have meters squared for area and then meters per second for velocity, which is going to get us meters cubed per second, or the rate of change of volume per unit time, a volume flow rate. So given that the fluid passing through this pipe has the same velocity at points 1 and 2, and the cross-sectional area of the pipe at points 1 and 2 is the same, we would have the same volume flow rate at points 1 and 2 as well. So we're looking here at volume flow rates. The volume flow rate of a fluid moving through a pipe is equal to the cross-sectional area of the pipe times the velocity of the fluid. This has interesting implications for a pipe that does not have the same cross-sectional area throughout. So, for instance, let's consider a pipe that tapers like so. And again, consider two positions, point 1 and point 2. Law of conservation of mass once again tells us that the amount of fluid that enters at position 1 with a velocity v1 would have to be equal to the amount of fluid that exits at position 2 with a velocity v2. In terms of volume flow rates, this would mean that the cross-sectional area at point 1 times the velocity at point 1 would have to be equal to the cross-sectional area at point 2 times the velocity at point 2. Now, in this example, with the tapered pipe, the cross-sectional area of the pipe is decreasing. So in order for the volume flow rate to remain constant, we would have to see an increase in velocity at position 2 versus position 1. So with this type of example of a tapered pipe, we would see that V2 would actually be greater than V1 in order to maintain the same volume flow rate at positions 1 and 2. And this equation then, A1 V1 equals A2 V2, we refer to as the equation of continuity.